Hello everyone, welcome to this session. Today we are going to discuss regarding the well hydraulics, especially today we are discussing regarding the steady radial flow in unconfined aquifers. As you remember, in the last session when we were discussing regarding the well hydraulics, we have discussed regarding the steady radial flow in confined aquifers. In confined aquifer, the water is trapped between the two impervious layers of ground, and how the water extract or water withdrawal take place and how the water drawdown occurs, then also how the water recovery is also can be seen. So that all part we have seen. Today, especially in this session, we are discussing regarding the unconfined aquifers. At the same time, we will try to correlate what is the difference between the steady radial flow in unconfined aquifers and confined aquifers. Let's discuss regarding the steady radial flow in unconfined aquifers. As we know that the analysis of flow in unconfined aquifers is more complicated than in confined aquifers. The scientist's theme also derived an equation for steady radial flow in unconfined aquifers, which are discussed in this session. Beside the basic assumptions and the assumptions of radial symmetry and steady state conditions mentioned above, the following additional assumptions are made in this case. What are these assumptions? The aquifer is unconfined and underlain by a horizontal confining layer. The well is pumped at a constant rate. The Dupuit Forchheimer assumptions are valid. Now here you can see that in last session we have discussed regarding the confined aquifer, where you can observe the water how it is trapped between the two impermeable layers and how this drawdown curve was obtained there. So these are the observation wells, and these are the radial distances of these observation wells from this particular well. So the same terminology that we are going to use in this session as well, only instead of this confined aquifer, now we are considering the unconfined aquifer, where the water will not be trapped between the impermeable layer, only it will be present on a impermeable layer. And you can observe here that this also we have discussed regarding how the water level or the head is obtained in this main well. So if you see the change in the unconfined aquifer, so here you can see this is the impermeable layer and this is the unconfined aquifer. Okay, here you can see this is the original water level is there. Above you can see the ground surface, right? So water extraction, that cube that we are going to deal with, right? So for any head on this drawdown curve, the radial distance r can be seen here or can be measured. So h0, it is the height of the original water table from the impermeable layer. Similarly, the other respective vertical distances are there. For example, if the water level in the well itself, it is a hw from the impervious level. Similarly, the head in this observational well from the impermeable layer, it is h1, and so as h2 in the observation well number 2. Okay, s1 and s2, these are the drawdowns observed at the observational wells in the s1 and s2, this observation well 1 and 2. Then what are the r1 and r2? All these are the radial distances from this main well. Now again, if you see here, if you compare regarding the confined aquifer versus unconfined aquifer, so you can see here the there is a change in the cone of depression as well as you can see this water level is raised above the this water level which is present in the confined water level, this particular, right. So in the this unconfined water table or unconfined aquifer, you can observe the static water table here, and there is no impervious layer present here, right. So and as there is no pressure is present between the any layer, so there is a difference between the cone of depression which is observed between these two confined and unconfined aquifers. So in today's session, these terminologies which is used for the discussion regarding the various equations, especially theme equation. So the same terminology has been used here. Only you can see from this main well, this is the water table which is observed in the main well, which is SW. Same terminology is there. Only the layer is not present in case of confined water aquifer. So same terminologies are there. I will repeat once again. So H naught is the height of the original water table from the impermeable layer water table in the well. It is observed as a HW. Then R1, R2, these are the radial distances. S1, S2, these are the drawdowns which is observed at the observational wells. H1 and H2 are the respective heads in the observation well number 1 and 2. So when we are discussing regarding this confined and unconfined, so in unconfined aquifers, the pumping will result in drawdown of the water table. In confined aquifer, the pumping will cause drawdown of the potentiometric surface. There is a change. All pores in the confined aquifer will still saturated. Now the flow equation is similar to what of confined aquifers, except we use H instead of the B. So Q is equal to minus 2 pi R KH dH by dr, where Q is equal to constant rate of pumping, R is equal to radial distance of the circular section to the pumping well, H is equal to saturated thickness of the unconfined aquifer, K is equal to hydraulic conductivity of the unconfined aquifer, and dH by dr is equal to hydraulic gradient. Now further discussing regarding the theme equation, if we consider that the first observation well is located at a distance RW, radius of the pumping well, where hydraulic head is HW, and instead of the second observation well R2, we will consider R2 is equal to R0, radius of influence, where drawdown is S2 is 0, and hence hydraulic head is H0, static and pre-pumping groundwater level. The theme equation can be written as there as a Q is equal to pi K in the numerator H0 square minus HW square divided by log natural R0 by RW. Now as we have discussed that we are considering the conditions here, H is equal to HW, R is equal to RW, and again at the edge of the aquifer, again H is equal to H0 and R is equal to R0. Then let's consider that the two observation wells are located in the unconfined aquifer at a distance R1 and R2 with hydraulic heads H1 and H2. Converting to heads H1 and H2 and the radii at two observation wells at locations R1 and R2, Q is equal to pi K H2 square minus h1 square divided by log natural r2 divided by r1. Rearranging the to solve the hydraulic conductivity, we want calculate the equation for the K is equal to, in the numerator, Q divided by, in the denominator, pi into bracket h2 square minus h1 square bracket complete multiplied by log natural of r2 divided by r1. Now here again, to calculate the, as we have seen in the earlier, in case of confined water table, so to calculate this Kf, so this equation can be obtained. So where the Q is in gallons per meter, Kf is gallons per day square foot, and R and H are the measured in the feet. So that equation, that 1055 Q multiplied by log R2 divided by R1 divided by H2 square minus H1 square. So only as we have discussed much in the case of confined aquifer, so there are some changes in the only this drawdown level and this you can say equation formation. So this we will have to observe, and accordingly we can calculate the discharge from the this unconfined aquifer and confined aquifer, where we have to consider the other parameters which are regarding the observation wells. So that's all from the today's session. So thank you very much for joining the today's session.